All right, we're picking up into our next topic in this unit is called the dot product. Funny story to share with you guys. I just finished recording this lesson, went to save it, and then realized that the microphone had been turned off the whole time. So I just had a half-hour lesson with no microphone. So this is now attempt number 2 at teaching this lesson. I really hope it works this time. Probably won't be any better though. We'll see. Dot product. Please don't tell anybody that story, by the way. The dot product is a calculation that we can make with Cartesian vectors and geometric vectors for that matter. This is an idea that someone thought up and said, hey, I have a really good idea. And it's important to remember that here. This is just a calculation that someone said, I think this might help with vectors. And it turns out that it will. So someone said, let's take any two vectors. We're going to align them tail to tail, like you see in the picture there. And we're going to refer to the angle in between. Remember, we've talked about that before. Whenever we're talking about an angle between two vectors, they have to be aligned tail to tail. And we're going to call this thing the dot product. So you can see the dot on the left-hand side. We're using the dot to represent this particular calculation. The way the dot product is defined is we're going to take the magnitude of the first vector, multiply it by the magnitude of the second vector, and times that by the cos of the angle in between. Okay, and that's all. This is something that's been defined. Okay, we're going to use this calculation and see what it does for us. And as we go through the course, you're going to see a little bit more. Okay, today you're going to start to see a little bit of the importance, but later on it becomes much more helpful for us. Okay. Here's our first example, and we want to just go ahead and try this. Right? Can we actually make a calculation of a dot product? So if we're trying to do A dot B, the formula says it's the magnitude of A times the magnitude of B times cos of the angle in between. Okay, that's what we're supposed to do. That's how the formula works. So the magnitude of A was 3, magnitude of B was 5, and the angle was 55. And if we do that calculation, we get an answer of about 8.60. And you'd look at that and say, well, what does that mean? Honestly, it doesn't mean much right now. Okay, we got an answer of 8.6. It doesn't correspond too much. It's not like we did a volume calculation or a surface area calculation, right? We didn't use quadratic formula. We did this random formula that somebody made up, and we got an answer of 8.6. It doesn't mean much yet. It will, but it doesn't mean much yet. Do keep in mind, though, that it's just a number. It's a number 8.6. It has no units. It's not kilometers, not kilometers per hour. There's no direction associated with it. It's just a scalar. It's 8.6. Now this example here is going to start to get to a point where it's a little bit more important. Here's P dot Q. Same formula, it's magnitude of the first vector times magnitude of the second vector times cos of the angle in between. So the magnitude of Q was 23, P was 23, Q was 18, and our angle this time is 90. And if you calculate that, we get an answer of 0, and it's exactly 0. Right? It's not close to 0 and rounded, it's exactly 0. The reason it's exactly 0 is because of that cos of 90. Cos of 90 gives us 0. 23 and the 18 made no difference. Cos 90 gives us 0. That's going to be helpful for us. So if we have two vectors that are actually perpendicular, if they meet at a right angle, then the dot product is going to be 0. Okay, now you'll see again in a minute why that's going to be a little bit more helpful. This is how we can make dot product calculations geometrically. So geometrically, we're given a picture, right? We're told particular magnitudes. We're told the angle in between. You might want to pause for a second because I'm not going to stay on this slide for too long, but this just summarizes a little bit what we've seen. It goes over that fact again that the dot product is giving us a scalar number. Right? We started with vectors, but we're ending with a scalar. That's significant. And then the 3 bullets at the bottom explain a little bit about what the answers represent. So in the last slide there, I said that 8.6 didn't mean too much, right? Well, what it does mean is in bullet number 1, it turns out that if the angle we start with between those two vectors is between 0 and 90, then the answer you get is positive. Okay, so the 8.6, the number wasn't important. The fact that it's positive was a little bit important. It meant that the angle was bigger than 0. If the angle is between 90 and 180 degrees, so we have an obtuse angle, now when you do cos of that angle, you get an answer that's less than 0, and so the dot product is less than 0. And the big one, the third one, if the angle is exactly 90, then cos theta is 0, and so our dot product is 0. Okay? So again, if you need to pause it, pause it. I'm going to skip ahead to the next slide, though. This is our first couple proofs today. We're going to do a monster one at the end, so just get yourself ready for a big one coming up. The dot product theorem. It says two non-zero vectors, u and v. Non-zero vectors means, they can't actually be the zero vector. There has to be some direction. There has to be some magnitude. They're perpendicular, and it's got an IFF. That's not a typo. That actually means something in mathematics. We say it means if and only if. Basically what that means is that you can read the statement forwards or backwards. Okay, so one way to read it is that if u and v are perpendicular, then the dot product will be 0. And then the reverse order, which is called the converse, if the dot product is 0, then the two vectors had to be perpendicular. And that's significant that it can go in both directions, right? Not all things can. If you think about rectangles, if I said a square is a rectangle, that's true in that direction. But if I go the opposite direction, a rectangle is a square, isn't true. Okay, some directions work, some directions don't work. So we're going to try and prove both. These are actually relatively short proofs. They won't take too much for us. But we're trying to prove both directions. So the first one says, if we can assume that the two vectors are perpendicular, can we convince ourselves that the dot product would have to be 0? So we start off with the formula we know. This is what we were told in the first place, right? The dot product is magnitude of the first times magnitude of the second times cos of the angle in between. Well, we don't know anything about vector u. We don't know anything about vector v. But we do know information about the angle in between. We're told they're perpendicular, which means the angle's 90. So I can put that in there. And if that's true, cos of 90 is equal to 0, and anything times 0 is 0. So u dot v has to equal 0. That part's proven. Second one is a little bit trickier. It's called the converse. Remember, it said we're working the opposite order. This time it's saying that the dot product is 0. Can we convince ourselves that the vectors had to be perpendicular? Start off the same way. There's our statement that we know is true. U dot v, this time that's what I know. I know it's 0. I don't know anything about u. I don't know anything about v. And I don't know anything about the angle in between. So all I've got is that 0. Well, this comes back now to kind of a grade 10 idea we would have showed you way before. If we're just multiplying, we do it that way instead. A times b equals 0. If two things multiplied together equals 0, the only way for that to happen is if a is 0 or b is 0. It's the only possibility. That's what we have here too. We've got three things. Magnitude of u is a number, magnitude of v is a number, and cos theta is a number. And if they're multiplied together equaling 0, the only way that can happen is if one of these three things was 0. Well, the first two we can rule out. Right? The magnitude of u and the magnitude of v can't possibly be 0 because we were told in the first place that we had non-zero vectors. So that's not true, and that's not true, which means cos theta has to be 0. The only way for that to happen is if theta was 90. And that proves it in that direction. Okay. So a couple little, I like those proofs. They're, get the point across. It's a proof, but it's not real long. What we've done so far is proofs, or excuse me, just dot products with geometric vectors. So if we see them, if we're told the angle in between, if we're told the magnitudes. Well, this chapter isn't about geometric vectors anymore. We're trying to deal more with Cartesian vectors. So as it turns out, there's a way of calculating the dot product given Cartesian vectors. So if I start off with a vector A and a vector B, like that, you can calculate the dot product using this formula. Okay, now remember, this initial one up top, this is the one that we said was defined. Right, we're going to define the dot product to be that. What I'm telling you now is that you can actually calculate the dot product this way too. Now, it's all well and good that I tell you that. We're going to prove that. Okay, and we're going to come back to it. We're going to do an example first. But that's a statement there that we want to prove. We're going to try and convince you that if this statement up here is true, that this one down here better be true as well. Okay, we'll prove that in just a minute. But it's a tough proof, and I want to do the examples first so that we're sure to get those out of the way. So this is calculate P dot Q. These two vectors are given to us in Cartesian form. So we could picture them a little bit, I suppose, try and imagine them on a grid. Vector P is 2, 5, so right 2 and up 5. But we don't need to in this case. We just want to go ahead and calculate the dot product. And the formula now says, this new formula, P1, Q1, first component times first component, plus P2, Q2, second component times second component. So that's 2 times 1 for the first one, and 5 times minus 3. So we get a 2 answer of minus 13. Once again, not really very exciting. Okay, we got an answer, it's a minus 13. It's a number, it's just a scalar, but it doesn't mean a whole lot. Okay, it's just minus 13. We'll try the same thing though for this example. And I'm not going to write the formula down again if that's okay. First component of the first vector times first component of the second vector. So 3 times 6 plus minus 9 times 2. And we get 18, take away 18, we get 0. That's much more interesting. So the minus 13, who cares? That wasn't that great. But to get P dot Q equals 0, we just finished proving that if that happens, those two vectors have to be perpendicular. And that's actually a really important characteristic for us, especially later when we start getting into lines and planes in three-dimensional space. Knowing if things are perpendicular is really, really helpful. Now, keep in mind, I need to compare that. I'm going to back up for a second. Compare that to this example that we did. We got an answer of 0 and said, well, they're perpendicular. That's not that exciting here because we were given the picture. So we knew they were perpendicular, right? The right angle mark was right there. But with Cartesian form, you're just given these two random vectors. You could try picturing them if you want, but it's far from obvious, I think, that those two vectors would actually be perpendicular. But it's a very quick calculation to confirm that they are. Okay? Now back up for 1 second. I said this minus 13 wasn't very exciting. It's not. The one thing that it does tell you, since it's less than 0, the angle between P and Q had to be bigger than 90. So it's somewhere between 90 and 180 degrees. Again, not that exciting, but technically that's what it tells you. An answer of minus 13, minus 14, minus 15 doesn't make much of a difference. It's the fact that it's minus that makes the difference. Okay, that wraps up calculations. Now we hit this proof. We are trying to prove that you can calculate the dot product by going A1, B1 plus A2, B2. That's what we're trying to prove. So what we were given was this statement, right? This was our definition of the dot product. We want to use that to try and convince ourselves that this is true. and we convince ourselves somehow that that's a true statement. Now, as I say, this is going to be a real tough proof. And so what I need you to remember as we're working through this is in no way something that you would just think up. Okay, this isn't a question I would give you on an assignment and say try and figure it out. Okay, it's way too hard for that. The steps that you take are not obvious steps, but some of them along the way I think you'll go, oh yep, that makes sense, and that's all I'm hoping for. Okay, we're trying to understand how this proof works. It is really important for you guys to start accepting this idea of we should be proving things. All through high school, we just tell you things and tell you they're true. Very rarely do we prove them or show you why they work. And that's going to change as you go further and further in math. It becomes much more important that things are proved rather than just told to you. Okay? So just keep that in mind. We're trying to convince ourselves that things work. Okay, how are we going to do it? So we need to change the right-hand side of that initial formula, that a dot b equals magnitude of a, magnitude of b cos theta. We need to adjust the right-hand side of that. The biggest problem at the moment is the cos theta. The cos theta is cosine of an angle doesn't help too much. So we need to use this diagram that we have to try and help with that. So the hint is, believe it or not, we're going to be using the cosine law. So there's our picture, and we're trying to transfer everything that we see in the picture into that cosine law. So we're going to be finding cos of theta and writing the cosine law out. Now, my recommendation always with the cosine law is think about what you're subtracting at the end. And what you're subtracting at the end is always the side across from the angle you're talking about. So we're subtracting the magnitude of vector a minus b squared. Okay, the other two sides are vector a and vector b, or I guess the magnitude of vector a and the magnitude of vector b. And we divide that all by 2 times magnitude a, magnitude b. So we've used that picture to create this cosine law. Now, what we're going to do is we're going to take this value and replace it in this original statement. Okay? Now, usually when I do this proof with a class in front of me, we use the smartboard and then we use a couple of chalkboards. So forgive me, I'm going to do my best to try and fit this all in here. Hopefully it'll work. It's going to be a little bit squishy, but we'll see what we can do. Get rid of that, and I'll show you what this looks like as we substitute in. Magnitude of a stays there. Magnitude of b stays there. And now cos theta gets replaced by this great big fraction at the bottom. And just take a look at it and see if you notice what's going to happen. So it's just the first step in a long proof. Oops, that's not a plus. There we go. And I am going to get rid of everything else. So we're going to need more space. So we've made the substitution using the cosine law. Do you see what's going to happen? There's the magnitude of a and the magnitude of b on the top, and the magnitude of a and the magnitude of b on the bottom. So those are all going to cancel out, which is at least a start for us. Starts to get rid of a few things. So we still have that magnitude there, still have that magnitude, and then this larger one, a minus vector b. And we still have a denominator. The denominator is just a 2. Now, I want you to keep in mind what the goal was. We're trying to get a dot b is equal to a1, b1, a2, b2. So we don't have any a1s and b2 is in there yet. So we need to deal with that. And what we're going to do is I'm going to jump to the next slide here for a second. We need to do some calculations on the side, and then we're going to come back and substitute into this place. But we just need to do some extra calculations for a minute. So one of the things we needed to calculate the magnitude of some vectors. And the way you get the magnitude of vector A was we used Pythagorean theorem. We did the square root of the sum of the squares of the components. So magnitude of A looked like that. But keep in mind, we weren't just subbing in magnitude of A. What you got there is magnitude of A squared. So that can be a little bit helpful. If I want the magnitude of A squared, that squared and the square root just cancel out. So you get that. And then similarly, if I wanted, the next one was magnitude of vector B squared, right? It's just B1 squared plus B2 squared. And so let's actually back up for a second. I'm going to substitute those in, okay? So back to here. This is equal to magnitude of A squared was A1 squared plus A2 squared, right? And then magnitude of B squared is B1 squared plus B2 squared. Okay, so we've got that. There's still this subtraction part that we have to deal with, so we've got more to do. So still aside, we need to worry about what vector A minus vector B looks like. Well, when we're doing subtraction, what we do is we're supposed to go first component, subtract second component, just like that. And then if I want to get the magnitude of it, in fact, I want to get the magnitude squared, right? The format looks just like it did for those two on the left. We take the first component and square it, and we take the second component and square it. And I'm going to move that down here for a minute because that's going to be a little easier. I actually want to expand this. Okay, so we're going to write it out. I actually want to do A1 minus B1 squared. So I'm going to multiply it all together. But we don't want to forget what it looks like. So there's expanded version. I'm actually going to do all the multiplication. Okay, so in this first one, we'll do A1 times A1, which is A1 squared. Then we'll go A1 times minus B1, which would be a minus A1 B1. But then you're going to do it again, right? The next one has the same thing. So we get a minus 2 A1 B1 in the middle. And then minus B1 times minus B1 is a plus B1 squared. Same thing for the second set of brackets. A2 squared so I want to take that and substitute that great big thing into that previous statement we had in the last slide. So I'm going to back up again. We are subtracting that big expression. It was A1 squared and we're about this point where we start to go, holy smokes, this really was a heck of a proof. We're actually about two steps from done. Take a look at what we end up with here and see if you notice what the good news is. And still all divided by 2. Put that back in. There's a lot there, but that whole bracket at the end is being subtracted, right? So there's this A1 squared, but then we're going to subtract an A1 squared. And there's an A2 squared, but we're going to subtract an A2 squared. And a B1 squared, subtract it. B2 squared, subtract it. Right? That minus sign means everything else in that bracket gets subtracted away. So almost everything disappears, except all those two A1 B1s and the two A2 B2. And there's a minus in front. Right? So the minus applies to both of those. So we get 2 A1 B1 plus 2 A2 B2 all over 2. And the 2's divide out. And in the end, we get our goal. This is what we were hoping for. That the dot product is actually equal to A1 B2, A1 B1 plus A2 B2. That's tough proof. That's a really tough proof. But the goal in there, remember, was just to be able to follow it. So if you're able to follow through the steps, you did a great job. If you had a little bit of trouble, just back up the video, give it another shot. remember, this isn't something that you'd be expected to come up with. It's just something that I'm hoping you're able to follow.